Okay, so welcome back. So, and in this session, we're going to learn something more about the tool. Okay, so as I told you before, this help us to apply what we will be learning in the theory. Okay, uh, using this S process tool. Okay, so let's do that. So already in the last lab class, we have copied this file, simple mass. We have seen the outputs. So far everyone know how to open this SWB, copy the example file and see the output. Okay, now let us learn how to give the inputs. Okay, so because see, as I told you before, in for TCAD programming, we don't write, memorize the code or syntax and we copy them. We will learn and will modify the existing syntax. That's how we're going to see. Okay, so we'll learn the concepts and we'll be able to modify the syntax to achieve what we want. Okay, so let's build a simple diode today. So before that, let us see the input and then we'll go and build a simple diode. Okay, so to see the output, you guys remember where to go? We have to go to the nodes. Okay, so to see the node numbers, you guys remember the entire thing is tree. Each row is called branch and each cell is called node. To see the node numbers, you can go here, view, tree options, show node numbers. So by this you can see the node number. So ninth node will have the result of its process simulations. Okay. So these are the variables will be used in the input. LG, NVEL, geox time, LED dose, and always the output will get stored in the last node of the particular tool. Okay. So say for S device, it will be stored here, not in this node. It will be stored in the this node. Okay. Anyway. Now let us see the input now. So let us open the input. So for the input, we have to go to the tool, right click on the tool, add input comments. Okay. So for the output, right click, visualize. We have done this last slide, right? So for the input, right click on the tool, add input comments. Okay. So this is a command which ran to get that output. Okay. So don't worry about this. This is what we're going to see. We will be learning almost all these commands in this course. Okay, so that you can able to build your device, whatever the device, it could be BJT, it could be MOSFET, it could be diode, using them. Okay, so this is what the input. Okay, okay. So now what we will do? Let us build a PNJunction diode. Okay, for that let us copy this file. It is not delete it. Just copy and create another file out of it. Okay, so let me call it a simple diode. We're going to build a simple diode. So for the diode, these parameters are not necessary. NVEL, GOX, LED, all are not required. So you can just select them like this, left click and select them, and you can just delete them. They're not required. Okay. And S device, no need to worry right now. Okay, let it be. No need to worry now. So whenever you do them, always better practice is right click, clean up the node output. It's always better to clean every time. Also, other way to do that is here, right click on your project name, your working directory, then project, cleanup, renumber the tree, cleanup. So this gives you full cleanup. Okay, that's better way to do that. Okay, so go here and clean it up. Okay, now open the input. Let us open the input. So how to open the input? Go to the tool, right click, add input, commands. So these commands, that's what you're going to learn. Okay, so for this one, let me just a minute. Okay, so now let us open the sorry the command input to this process tool. So for that, already we opened it, right? So it's there in the gedit file. Okay. So now what we will do? Let us learn the first location. This line x line commands. Let us learn in today's class. Okay. So for that, let me open the PPT. So for your better understanding, just a minute. Okay. So see, for our silicon, for the processing, our starting material is going to be the wafer. So wafer, how the wafer comes, we will discuss the theory, don't worry. So it will be a circular plate, thin, it will be thickness of 500 microns. Okay, so this is the wafer. So after processing, we will have all the circuits in them, which we call die. Okay, so this is the processed wafer, the unprocessed wafer. Left side is your unprocessed wafer. In this course, we're going to learn the processing. What are the process we'll be doing on the wafer? So today we'll be learning how to make small PN junction in this unprocessed wafer. Okay, so we'll be doing using simulations today. Okay? After processing, it will be like this. So you'll be having a small circuits. You cut them, you pack them. That is how your chip comes. Okay. So we're going to for the simulation, we're going to take a cross section of it, and we're going to take a small piece out of it. Okay, because the wafer will be 6 inch, 4 inch, 6 inch, or 8 inch in diameter. Okay, so we're going to take, but for simulations, it's very difficult to simulate such a big domain. So we're going to take a small portion of the cross section. You're not taking on the surface. Please understand. You're taking a cross section. Okay, that small rectangle that is going to be here. Okay, so here, so the top is your top surface. Okay, this is your bottom surface, but we're going to take a very small portion of it, and let me show you the axis. Okay, this is how the axes are being defined in this process. Any guesses? So normally we take horizontal as x, vertical as y. Here it's going to be ulta. Please remember that. So the horizontal axis is going to be your y-axis, and your vertical axis is going to be x-axis. Okay, please remember this. And you should also see that the x-axis, I mean the vertical axis is going downwards. It means it increases down. Normally we draw upwards, right? It means 0, 1, 2, right? But here it's going to be downwards. So 0, 1 is not upwards, 1 is downwards. Okay, so this you have to know. Now, so I told you before, you're going to take a small portion. So I'm going to take 1 micron width, 2 micron depth. Actual depth is 500 microns. I'm going to take a very small portion for the current processing. Okay. So 2 micron depth, 1 micron width. So now to define that. Just you have to define the points. Okay. Assume this point is 0, 0. 0 is your x, x comma y. Always that will have x comma y. It means your x axis comma y axis. Not okay. So in this case, your vertical coordinate will be on the first coordinate. Okay, so always x comma y. So 0 comma 0. Now what will be this point? Let me take a highlighter. Always a pointer. And think, just a pause the video and think what could be this point, and then come back. Okay. So this point will be, see, this is your y movement, right? So y is going to be how much? I told you width is 1. So it should be width of 1. So y should be 1 on the same height, right? Depth is same. So the point is what? 0 comma 1. Similarly, what could be this point now? You can make a, maybe pause the video and see. So answer is, so we're going to make what? Depth is 2 microns. So x will be 2. Y going to be in the same, in your same y-axis, right? So y will be 0 still. And what will be this coordinate now? Then? So this coordinate will be 2 comma 1. Okay, so this should be very clear because these numbers will be feeding your program now. Okay, and then okay, let's feed it and then let's come back. Okay, so let's feed this. So I told you this is like line x, location 0. So the x is going to have width of 1. So already it is width 1. So no need to worry about it. So you can even remove the middle line for now because we're going to assume uniform spacing right now. So no need of middle line. Later we'll see. That is for gradient meshing. When you have to do meshing, I told you previously, meshing is like we're going to discretize the domain, right? So for that, we'll be taking few finite number of points, right? So the spacing between these points was defined here. Suppose sometimes we want very fine points at certain places, we can do gradient meshing. At that point, we will have more points. So in that case, we can have more number of line commands. Right now, let's keep things simple. Let us have uniform spacing. I'll come to spacing, don't worry. Right now, you just worry about this starting line and the ending, this one. Spacing and tag will come to that, don't worry. So x is 0 to 1.0. What about y? Y is 0 to width, right? Y is 0 to 2 micron. So remove this all other things. That at LG is, what is this means is, whenever you have something with within at, you are instructing the SWB like this variable is being defined in the workbench. You are instructing the interpreter to take the value from the SWB. Okay, so whatever between that. Okay, so again I'm removing the middle line right now. So because I'm not going to gradient meshing. So gradient meshing. So here you can see the x is 0 to 1 micron depth. Sorry, x is vertical, right? Sorry, I made a mistake here. So x should be 2, y should be 1. Sorry, because x is your depth. Please remember. So it's going to be 2 micron depth. Y is going to be your width. Okay. So let me go back now for the spacing explanation. Okay, let me go back to the PPT. Okay. So we have defined the x and y. We also fed those parameters. 1 micron. This specification has been given into the command now. Okay, the line command, right? The top. So we have given 0 and 2 in 2 lines and 0 and 1 in another for y, for the y dimension. So that's what you have to change. Okay. Now comes the spacing. So I told you, see this rectangle is just for the guide for our eyes, but actually they are not actual line. That would be what they are discretized. You will have some what to say. You will have some fine number of points in there. For the computer, it's never continuous. Always it's discrete. Okay. So the computer will only see the red dots. For our eyes, we see the complete just for visualization aid. Okay. Fine. So here only those equations also getting solved. So now these are the meshing points. Now we have to define the spacing between them. Similarly on the y-axis as well, and fully for the entire device. So y x spacing and y spacing have to define. So this is the distance between them spacing. So it's 2 micron depth. I told you, right? I want 20 points. So how many? What is the spacing roughly? It's 2 micron depth. I want spacing. I want 20 points at least. So 20 points, how do you do that? So 2 divided by 20, so how much points you will get? 0.1. So spacing you can do 0.1. Similarly, it's 1. I want at least 10 points. So what is the spacing? Again, 0.1. So let us give this spacing in the command. And also the next thing is the tag. It's small additional. So tag is, so for x equal to 0, so which is the top surface? This is the top surface, right? So this is the top surface. So let us give tag as top here. And this is the bottom surface. So let us give tag as bottom here. Okay. So for when x equal to 0, that is top. The tag is top. For this one, the tag is bottom. Similarly, this one is left. This is right. Okay. Tags are very useful. We'll be referring them later. Just a label for the surface. Okay. So these are the things you're going to now program it. Okay. In the process commands. Let's do it. So spacing we found. Let us have 0.1, but that's very less spacing because we randomly choose 20 points, but better to have more points. But for the initial simulations, better to have this 0.1 spacing. So x equal to 0, you told, we know that that's tag equal top. When x equal to 2, that's a bottom point, so tag is equal to bottom. Let it be as the same. Similarly for y location also, we found the spacing to be 0.1 right now. Later we may increase. Okay, that's it. Now you understand these few lines, right? So you define the x, the depth, y, dimensions of your substrate. This is your unprocessed wafer. And now we're going to use these tags to define the substrate. See, that's the next line. Region. This entire thing is made up of silicon. Suppose you want to make a germanium substrate, you have to write germanium here. Right now, it's going to be silicon. X low, top. Xi, this is the syntax. Okay. So we will be linking those tags to your region. Now we have created a substrate. That's what we have done with this initial 5 lines. Is it fine? Okay. So then this init concentration is, see your wafer is already, even though I say it's unprocessed wafer, while growing process, while the method to grow the wafer itself, it's already doped. Only doping is done. So they are uniformly doped. Okay. So that information has to be fed. So generally the doping will be around 10 power 15 or 10 power 16. And what type of doping? So there are p-type wafers, there are n-type wafers. Let us assume today's session, let us take a p-type wafer. Okay. So The initial concentration as given the PPT is going to be 1E15. 1E15 means 10 power 15. Okay, and boron is P-type dopant. We will come to this, what it means. Right now, this information is enough. Okay. So what we have done, we have created a slab, a small piece of silicon, and we have initialized the doping concentration and what type of dopant. So boron means it's a P-type wafer. Phosphorus or arsenic means it's an N-type wafer. Anyway, we will be discussing it in the course as well. And now we can remove unnecessary lines right now. So I will suggest you to remove till till this line, implant phosphorus line. Just delete them. Anyway, we have a copy of them. So this tells you, this PDB set tells you the charge transport, the dopant transport mechanism that once we started the theory, you will understand them better. So right now, don't worry about that. It should be there, or you can even delete them because the default doping diffusion model will be enabled by default. So you can have them or delete them. It's your choice. I'm keeping them just to remind them that the differential equations running begin. Okay. So this is the equation will get solved. The charge for me, the differential equation will get solved to model the diffusion transport. Okay. So we are still learning about process simulations, how to use them. Okay. Now implant doping can be done by two ways. One is gas phase diffusion or solid phase diffusion. Other is implantation. Implantation is unit 2, but anyway, let us use this command. Don't worry, implant will be discussing them in detail in the theory classes, so don't worry about them. So implant is just one way of doping them. Now we took the wafer, we started doping them. Implant is we put dopants, we strike the dopants deep into the wafer. Okay, not deep, near the surface of the wafer. Okay, so we strike them. That's what implant. The dose tells you the number of dopants. Energy tells you where you're going to place it. Even if you want to deep, we can do deep implantation also possible. So we are using energy 15 that puts you somewhere near to the surface. If you want deeper, you have to increase the energy. Okay, anyway, that's for unit 2. Anyway, just to understand, I told you slightly about this. After implantation, you have to activate the dopants. To activate the dopants, you have to heat them. I told you, right? How do you form? How do you make dopant to go inside? Heating is required, right? The heating step is done by this command. Diffuse, time. So you have to give at least 100 seconds for now, and temperature is fine, 1000 degrees Celsius. The default unit is Celsius, not Kelvin. Please remember that. It's Celsius. And then we are going to deposit some metal as well. Let it be as it is. I'm not going to change. Deposit will come. Mask, deposit, edge, all the part of lithography steps. Okay. So we'll be learning it, but right now let it be. So one small change we make. So what I'm going to do is, uh, I'm going to make this as 0.5. I will let you know what I'm doing. I'll shortly tell you what I'm doing here. Just note it down. Just do what I'm doing here. Later I'll tell you what exactly is happening. So mask, just give 0.5 because depth is going to be 1. I'm just taking a mask off of it. Okay, nothing, there's no big math here. Just off of it, I'm taking as a mask. Okay, so what have we done is we have taken a wafer, we doped, we deposited aluminum, we made a mask of 0.5 from the left, and we're going to etch the remaining portions. Okay, so let's see. This transform, reflect, and contact commands right now not required. We'll be using them later, and that's it. Okay, so we that's it. So you have to just run it. Okay, let's run it. Go here, select here. So to view, let us give the node numbers also. View, 3 options, show node numbers, click here, run, give okay. Okay, let it run. Always just have to double click and see. So you can see N1 is your node number 1. Double click and see what is happening. So it is taking the syntax. So it will take some time to run. It will solve the equations. Okay, the differential equations for the diffusion mechanism. And also for implantation, right? Implantation also has some bunch of equations to be solved. And the time of simulation depends on number of points. We have given very less number of mesh points because number of each point those equations will get solved, right? So it will run faster. Okay, let's see. So it's doing implantation is done, diffusion is started. You see, diffusion is over, and then only one step, deposition of aluminum. That's all. Let it run. By this, we have made a PN junction. Okay. So for every, we are going to put 100 seconds, right? So it's running. So 18 second, 35 second, 1 minute, and it's done almost. Simulation completed. So don't worry about the warning right now. Let us go here. So once it turned yellow, it's done. Now right click, visualize to see the output. Remember, you have to right click on the node, right? Select file,